Hi everyone, this is Karen B, and in this video I will do my best to give you the most comprehensive explanation of how the sun sets and rises on a flat Earth. This is the most commonly asked question by people new to questioning the standard heliocentric model. I took this video on July 27, 2017 in Myrtle Beach, South Carolina with my P900. For me, this video was instrumental in my understanding on how the sunrise and sunset work on the flat Earth, and I'll show you why in a bit. Early on in the flat Earth community, the most common answer to this question was simply perspective. While this does play a part in how day and night work on flat Earth, it's not the only thing at play. There are a few different things working together in harmony to create day and night on our plane. First, on a flat Earth, the sun is small and close, a local light about the same size as the moon. Most people first picture Earth as a disk in space with a large sun far away. Don't mix models. We don't believe the Earth is a disk floating in space. To understand, you need to forget about space as it has been described to you. The Earth is a plane with the luminaries within our atmoplane and our small local lights. This is an example. Now, I'm not claiming that this is what Earth actually looks like. This is just a visual to help you understand. So, first, let's examine perspective. Perspective is the representation of how an image is seen by the eye. It's about how the angle and distance of a three-dimensional object is represented on a flat surface. Here we have our two horizontal planes with a perspective grid over it. You can see the trees rise up toward the horizon and get smaller in size, and the clouds appear to get lower in the sky as they appear to converge into the vanishing point. The clouds seem to drop toward the ground in the distance, yet we know that the clouds are still thousands of feet above the Earth's surface. The same thing with the sun. It is always high above the Earth's surface, but seems to touch the ground as it reaches a distance outside the limits of our optics. As the sun moves farther away, the horizontal planes will appear to merge. So here, we have our observer on the left looking off as far as he can see. When you, as an observer, stand looking as far as you can see toward the horizon, the sky plane and the plane of the ground you stand on appear to converge at the end of your eyesight in the distance at the vanishing point. When inland, there are many features on the Earth's surface that create an artificial horizon. For example, if you live in a valley, the sun will set behind the mountain and disappear from view much faster than if you live in an area with no hills or mountains or next to a large body of water. Where I live, there are many trees surrounding me, so the sun disappears behind them long before the daylight fades, and since we are told almost from birth that the sun is going on the other side of the ball, most just accept it and don't ever give it a second thought. The next thing that causes the sun to set and rise is our atmosphere, or atmoplane, as I like to call it, since we live on a plane, not a sphere. There are multiple substances that make up our atmoplane: nitrogen, oxygen, argon, carbon dioxide, and importantly, water vapor. Water is the third most abundant substance in our air. Water also has a great effect on light and how it propagates through the air. Think about the ocean. There are many layers of visibility. First, you have the sunlight zone, which is the top layer we are in the most, and it's still easy to see in the water while the sun is overhead. Then you have the twilight zone, and the light is now less able to penetrate the water. After that, you have the midnight zone, where it is too dark to see even at high noon because the light can no longer go through the layers of water. The same thing is happening on our Earth's surface, but at a much larger scale. Clouds and water vapor obstruct the light of the sun, and it can no longer illuminate your area. This is a clip from a video made by my good friends Zach and Steve. In this animation, Steve rendered the stars over a flat Earth. The top is rendered with the atmoplane and the bottom is rendered without, showing how perspective alone does not explain how the luminaries appear to go below the horizon. Those are the basics. You can stop here if your questions were answered. If you want to dig a little bit deeper, keep watching. How does the atmoplane make the sun and other luminaries appear to set below the horizon? The water vapor in the air acts like a lens. This is called atmospheric lensing in mainstream science and is explained here.
The science is the same of that of a lens. Here's a simple example.
So if you're looking at Chicago here, just maybe now you can just see the top of the Sears Tower, and if our simulated temperature inversion moves into place, hopefully now you can see pretty much all of Chicago,
see all the lower buildings,
including what's at ground level.
So the atmosphere really is acting like a lens.
Yes.
So not only does the water eventually obstruct the light, but all the billions of tiny water droplets behave like a lens. You can emulate this with a lens and a light source like I do here. This candle will take the place of the sun. Watch as I slowly move it back in a straight line, and also it stays at the same height since I have it placed on this mason jar. The atmoplane and your vision create what we call a personal atmoplanic dome, or personal atmospheric dome if you please, which is the shape of the lens dictated by our eyesight. This simulator, ironically made by a globe Earth believer, shows how this works. It's not perfect, but it certainly is close. This can give you a better idea of how the sun can set visually without having to go behind an imaginary curve. Okay, I want to go back to my sunrise video and take a look at how light reflects off of a flat surface. I went to this online tool that lets you create different simulations of a light source and a reflective surface, and this is simulating the sun over flat water. The light is radiating from the center of the source out in all directions. Look at how the light rays bounce off the reflective surface and off to the distance at an acute angle. So here's our observer again, and you can see the reflected ray reaches our observer before the source does. This is what creates the effect we see at sunrise or sunset. The first thing we see is the reflection of the sun, not the actual sun. The light of the reflection is closer to us, so we see that before we see the sun itself. Watch in this video how the sun's reflection begins to come into view, and it's not round, it's squashed, because it's reflecting at a sharp angle. There's a line here where the angle of the view is so sharp, the water becomes a mirror and it's reflecting the sky. So when the sun approaches you and gets close enough for your eye to see it, the disk appears to rise up from the reflection because visually, it is now within the limits of your eyesight. As the sun moves closer, you see the reflection remain below the disk for a short time, and then it's gone. This can only happen on a flat surface. Here is an example on a smaller scale. Watch as this little ship comes between the observer and the big ship, showing you how the reflection is closer to you than the object itself. And that is how the sun sets and rises on a flat Earth. If you're new to Flat Earth and you have questions that you want answers to, leave a comment below, or you can also join 24/7 Flat Earth Discord. We have 25,000 members and lots of knowledgeable people who are willing and able to speak with you directly and answer any questions you may have. Thanks for watching.